This video is about units that are used in chemistry and in science in general, and that you will also see when you are in your future careers, whether it be in nursing, dental hygiene, or rad tech. Scientists have agreed on a set of international or standard units, and those are metric, and you will hear me refer to International Union of Pure and Applied Chemistry. That's IUPAC. You'll also hear me refer to the SI units or the System International or International System. Some of the basic units that we'll be using are going to be the meter, which is for length, the gram, which is for mass, the liter for volume, and time seconds. All of the metric units in the SI system are related by a power of 10. Phew, it's nice and easy. It's not 12 inches to a foot. And the power multiplier is indicated by a prefix. So that prefix could be kilo, centi, mega, milli, and the prefix multipliers are always the same, regardless of the standard unit. So what that means is if I have a kilometer or a kilogram, both have a kilo as the prefix multiplier. One of the things that you'll have to do in this class is report measurements with a unit that's close to the size of the quantity. So for instance, if I have something that measures 2,500 meters, I would write that as 2.5 kilometers. One of the things we'll cover is how to convert between units and then to kind of understand the magnitude. So this is the common prefix multipliers in the SI system. Some of these you'll have to memorize, and I'm going to write here the ones that you have to memorize. I'll highlight them in green. You don't have to memorize all of these. If you go into the STEM field, so let's say you're going to go pre-med and you decide to go through biology, physics, and organic chemistry, you will have to memorize all of these. For nursing and allied health sciences, you just need to memorize a few of them that you'll see on a common regular basis that you'll need to know. I'd like to go through all of these, give an example of where you would find them being used in just the regular world. Mega, you might have seen Mega Man. Mega is used typically in the radio signal. If I'm listening to radio at 90.3, that's 90.3 megahertz. That's the frequency of the radio signal that I'm listening to. And it's large, it's times 10 to the 6. So it's 90.3 times 10 to the 6 or 9.03 times 10 to the 7 hertz. It's large. Kilo is one that you'll see and that you do need to memorize because kilo is the common prefix multiplier that you'll see for body mass. Someone could be 75 kilograms, or a baby could be 3.5 kilograms. Medication is often dispensed as milligram per kilogram or microgram per kilogram. Body masses always have to be expressed in kilograms. And this is times 10 to the 3. So what this means, base times 10 to the 3, if I have 7,500 grams, then that is 7.5 times 10 to the 3 grams or 7.5 kilograms. So there are 1,000 grams in every 1 kilogram. And that's what the 1,000 means here. Deci is one that we really won't use much in chemistry, but I've seen it a lot in the nursing calculations book. So I'm just going to highlight this as something that you should remember. And it's the negative one. So now we have this split between something that's larger than 1 and something that's smaller than 1. So these above here are larger and these below are smaller. You'll often see deciliters as a dosing value, 1/10 of a liter. So maybe you're supposed to give someone 1 deciliter, which is 1/10 of a liter. So 1/10 or 0.1 of a liter would be the value of a deciliter. Centi is common. It's used in chemistry quite a bit. And it's also used in nursing. And one of the ways that you'll see it in nursing is in centimeters cubed or cc's. So it's a volume measurement, cc, which is equal to centimeter cubed. You'll also see it in length. So there are 2.54 centimeters in 1 inch. So it's common that lengths, heights are measured in centimeters. And there are 100 centimeters in every meter. So it's 1/100th or zero point zero 0.01 of a meter on a ruler, like a meter ruler. Sometimes you call it a yardstick. But if you had a meter stick, you would see 100 centimeters on your meter stick. Milli is also very common. This is one that you'll want to memorize. The most common way that you'll see it is in volume, milliliters. There are 1,000 milliliters in every 1 liter, or 1/1000th of a liter. That's what a milliliter is, or 0.001 1/1000th times 10 to the minus 3. So definitely want to memorize that one. The next one, which I'm going to recommend memorizing because you'll see this one in biology. You'll be using a microscope. Microscopes are used to measure objects that are on the micrometer scale. You'll also see this you'll see micrograms per kilogram for dosing. You'll see microliters, and it's 1/1,000,000th of a liter. If you are looking at your meter stick and it's got 100 centimeters on it, the next thing you see is millimeters. Okay, so you can see little millimeter markings, but between the millimeter markings, it's too small for you to see. So you actually do need to use a microscope, and that is 1/1,000,000th of a meter, or 1/1,000,000th of a liter. The next two, I'm not going to ask you to memorize, but they are important in chemistry and in physics. So nanometers, the distance between two base pairs is roughly 0.1 nanometers. And actually, so you'll notice here that I wrote 0.1 nanometers. That actually has its own unit that's not listed on here. I'm just going to mention it, the angstrom. The angstrom is used a lot in biology, and you could say that a base pair is anywhere between 1 to 10 angstroms apart when you're looking at DNA. This is also useful, nanograms, nanoseconds. A lot of things happen on the nanosecond time scale. And then pico. Pico is really useful when you're talking about parts per trillion or parts per million concentrations. If I had a contaminant that was in the parts per trillion contamination level, it would be on the picogram to gram level. So there are also some other SI unit. We are using storage now in the gigabyte and the terabyte. Those are some other metric units. So new SI unit prefixes for use with very large and very small numbers were adopted. And this was the year of 2022. The mass of the electron can now be described as being approximately 1 rontogram. That is a very small number, 10 to the minus 27 grams. And interestingly, electron masses are so small that electrons weren't even discovered until the 1900s. For the time being, you do not have to memorize the rontogram. There are several common English units and metric equivalents. You do not need to memorize these, okay? I will give every single one that you need to know on any sort of assessment, whether it's a quiz or an exam. And then if you're doing homework, you can look it up. So first of all, let's look at length. Length is the distance between two objects. Here's my foot. I'm measuring my foot against the standard British foot and the British yard. What you'll notice here, we've got the kilometer is approximately 0.6214 miles. The meters, 39.37 inches. The foot is 30.47. I'm just going to say that this one right here, 1 inch is 2.54 centimeters exactly, is super helpful to memorize, even though I'm not going to ask you to. You may be using that one a lot. So 1 inch equals 2.54 centimeters. And notice that word exactly. What that means is that this is a definition. So all of the metric prefix multipliers, all of those conversions are defined, and they will never impact the significant figures in your final answer. That is the same case for 1 inch equals 2.54 centimeters exactly. More common English units and their metric equivalents that you do not need to memorize are for mass. So mass is the amount of matter in an object. And one that's going to be really common that you don't have to memorize, but you might want to just because you'll use it a lot is 1 kilogram equals 2.205 pounds. Some other ones that we'll be using in this class that I can give you, 1 pound is 453.59 grams, and 1 ounce is 28.35 grams. Here I have on the right something that's very interesting. This is known as the IPK. And this was in 1889, the SI unit of mass was the kilogram, has been defined as being equal to the mass of the International Prototype Kilogram, IPK. The IPK is a cylinder of platinum iridium alloy that sits in the International Bureau of Weights and Measures near Paris. New standards for what the kilogram is was defined on May 20th of 2019, and this IPK was retired. There were actually 5 international prototypes around the world, and that's really important because people had to compare the kilogram that they had in their lab to the kilogram that was standardized around the world. And now it's actually a constant that's being used, Planck's constant. But again, it's really important that there is a standard way to understand what a unit is. Another common English unit and their metric equivalents is for volume. So I have here something that looks similar to what I have at home, a measuring cup. Notice that it's in cups and it's in ounces. If I am using a recipe that is from outside of the US, my units will be in things like milliliters and liters. 1 liter is approximately 2 pints, 2.113 pints. This one's really useful, and I'm going to rewrite 1 liter equals 1,000 cubic centimeters. I'm going to rewrite that one because we will definitely want to know that one and memorize it. Is that 1 milliliter equals 1 centimeter cubed. Sometimes it's called cc's. And then there's some other metric equivalents for volume. I just wanted to put here, this is kind of small, but if you go to the Institute for Safe Medication Practices, one of the things that this institute is designed to do is to prevent errors in delivery medication to patients. And so I have this here. You can check this out online if you want. It's also going to be available in the nursing books that you're reading. Here's one. I just talked about the cc, which is the cubic centimeter. It's sometimes mistaken as units. And so the best practice is to use milliliters. And sometimes you'll still hear people say, I need this many cc's. Written, the cc can be confused for units, and a unit is different than the volume measurement of a cubic centimeter. So remember, I just wrote down that 1 cc equals 1 milliliter. So it's better to use the unit of milliliter. IU is international units. Sometimes it's mistaken as IV or the number 10. So just use units. So international unit is the unit. Here's another one that you need to be careful of, the L or the ml. So the liter, the lowercase l is mistaken as the number 1. You want to use the uppercase L for liter. And that is something that's really important. When we write liters, we always write an uppercase L. And then sometimes people don't write that uppercase for milliliters. You always want to write little m, big L. And the reason you don't write big M, big L is big M is mega, which is times 10 to the 6. And little m is times 10 to the minus 3. And that is a billion times different. So don't ever write big M when you mean little m. And again, or million, another mistake is going to be here. I was talking about that big M is mistaken as 1,000, use million. K is mistaken as a million, use thousand. You'll get to this in nursing. I just wanted to point it out here that it's super important to start developing the proper use of units now. When you're in your nursing program or the next classes, biology, it will be a lot easier for you in those next classes. This is a concept check to ask you to identify which of the following units would be best to measure each of the items below. The centimeter is a unit of length. The milliliter is a unit of volume. The kilogram is a unit of mass. And the microsecond is a unit of time. So go ahead and see if you can identify which of the following units would be best for each of the measured items below. All right, so for question 1, the mass of a large sack of flour, that's about 5 pounds, maybe 10 pounds. So if you had a 10-pound sack of flour, that'd be approximately 5 kilograms. So I want to use the unit kilogram for number 1. For number 2, it's a volume of a handful of water, and that's milliliters. And a volume of a handful of water is about 5 milliliters. The amount of time it takes for gas to move through liquid, question number 3, this is a time. So this is going to be the microsecond. So gas diffuses really quickly, and that's really important. We want oxygen to diffuse into the cells, carbon dioxide to diffuse out of the cells really quickly, and it only takes microseconds. And the length of a caterpillar. So a caterpillar could be maybe like anywhere from an inch to a couple of inches. And that would be around 10, maybe 10 centimeters or something. So centimeters for the length of a caterpillar. There is a systematic approach to problem solving. And this is it on this slide. It's very full of words. I'm going to go through these steps one by one. Step number 1 is to identify information from the problem. That is what's given or known. We want to know the quantity and the unit. So we always have units. What is unknown? Any relationships, and this is going to be things that are implied in the problem or maybe things that you have memorized. The next step is to design a plan. And honestly, sometimes in designing the plan to solve the problem, you find the relationships. Sometimes you don't know that you need certain relationships. That's fine. Also, I sometimes work backwards, and those relationships can be conversion factors or maybe equations that I need. Step number 3 is I will apply the steps in the conceptual plan to solve the problem. I need to check that units cancel properly. And this is where I'll be using dimensional analysis to solve problems. And I keep all my units in my problems. And I have been known to get down on my knees and beg students to keep units in their problems because this is how it's a pretty fail-safe way to solve problems. And I really want everybody to succeed. So please write your units in your problems. And then in terms of how to do the math, you multiply across the top and divide by each bottom term. And in the TI 30X 2S, you can use parentheses or you can go step by step and hit enter in between each one. The final step is to check to see that the problem was solved correctly. So 1, the unit at the end is what you wanted, and that the size of the number is reasonable, that it's not out of the scope of what you're solving. So this is another look at how to solve problems. This comes from the book Calculate with Confidence in the nursing program. Almost exactly the same thing. Something that I like about this one is similar is eliminate unnecessary information. Sometimes there's unnecessary information, not that much in our chemistry, but there may be in the nursing field or like maybe on your nursing exam. We always want same system of measurements and units. That's really important. And we also, we're looking at the medication label. I actually have some medication labels to do some practice with in a video in the Math Plus Chem videos that are on the Canvas shell. Consider reasonable. This is doing our calculation check and then labeling the final answer. So tablet or capsule. And then something I want to point out in medicine that's different in chemistry is they don't use significant figures. They're going to be using 1.5 or half instead of 0.5 and 1.5. And that's totally unique to nursing. In chemistry, we're making measurements in a lab. And in nursing, some tablets can't be cut in half. If they're enterically coated or they're time release, they can't be ground up, they can't be cut in half. That's something that you'll have to consult with the doctor or through your education in the nursing program. So we'll follow similar steps, but we will also be making sure that we're paying attention to significant figures because we're talking about chemistry in this class. I mentioned equivalent statements and conversion factors. A conversion factor can be generated from an equivalent statement. The equivalent statement will have a equal sign in it. So an equivalent statement, 1 inch equals 2.54 centimeters, can be written as conversion factors. And you can write two of them. So 2.54 centimeters, 1 inch this way, 1 inch equals 2.54 centimeters. And you might look at this and go, whoa, those aren't equal to each other. Well, mathematically, if I didn't have the inch and centimeter written on there, they aren't equal to each other. But as an equivalent statement, these are both equal to 1 because these are equal to each other. This is another reason it's really important to keep units next to your numbers so we won't have any naked numbers in our conversion factors. In this example, a patient receives 1750 milliliters of fluid. How many liters are received? A little typo there. So what I know is that the patient received 1,750 little m big L. What's unknown is how many liters is that? My concept map will go from milliliters to liters, and I'm going to using a CF. CF is a conversion factor. And I know that I have in 1 milliliter, 1 times 10 to the minus 3 liters. That's my equivalent statement. So now I'm going to set this up starting with 1,750 milliliters. I'm going to write a conversion factor and I'll put some big brackets around here. And this is a multiplication in the middle. I need to cancel out milliliters, so milliliters goes on the bottom, and I want liters, so liters goes on the top. So now I'm going to write the number that's in front of the milliliters on the bottom, so 1. The number that's in front of the liter on the top, 1 times 10 to the minus 3. And I'm going to check my units. So milliliters on the top cancels with milliliters on the bottom, and I left with liters. And that's the unit that I want. So that's a great, I just did that little check right there. And I plug this into my calculator. I get the answer 1.75 liters. This definitely makes sense because another way to think of the milliliter to liter conversion is that there are 1,000 milliliters in every 1 liter. And this is 1750 milliliters, so it should be 1.75 liters. In this example, an individual is 4 feet tall. How many, another typo, centimeters tall are they? I'm going to write down what I know. I know 4.0 feet. That is a number with 2 significant figures. And what is unknown is how many centimeters tall are they? So starting with feet, and then I'm going to convert to centimeters. So I actually have 2 conversions I'm going to do because I know information about feet to inches there are 12 inches in 1 foot, an equivalent statement that I will use to make a conversion factor. Inches to centimeters, in 1 inch, there are 2.54 centimeters exactly. And also the 12 inches to 1 foot is exact. And I'm going to need some conversion factor out of that equivalent statement. I'm going to start with what I know, 4.0 feet. And some people write this over 1, but you don't have to. And I'm not going to. And I'm going to multiply using this equivalent statement up here with feet on the bottom and inches on the top. The number in front of the foot is a 1, so I'll put 1 foot on the bottom. The number in front of inches is 12 inches, so there are 12 inches in 1 foot. And then that will cancel out the feet. The next conversion I'm going to do is from inches, so inches has to be on the bottom to cancel, to centimeters. And the numbers are 2.54 centimeters on the top to 1 inch on the bottom. So I'm just going to check to see what units cancel out. Feet cancel in the first step. The inches cancel in the next step. Centimeters doesn't cancel with anything. It's left all by itself. So I'm going to say 4 times 12 times 2.54, and I get the answer 121.92 centimeters. And then I just have to look at the information to see how many significant figures I have. This number 4.0 has 2 sig figs. The conversion 12 inches to a foot is exact, and so is 2.54 centimeters per inch. So our answer is going to be limited to 2 significant figures, and I'm going to rewrite this as 120 centimeters. And that's using the significant figure chemistry perspective right there. Here's another example. In this example, a baby weighs 7 pounds, 8 ounces at birth. What is the baby's weight in kilograms? So what I know is 7 pounds, 8 ounces. What is unknown is the mass in kilograms. So I do have a pound to kilogram conversion. I also have an ounce to pound conversion, but I don't have something when they're like pounds and ounces combined. So my very first step is actually that I need to convert that 8 ounces to pound and find the overall mass in pounds. And then the next step is to convert from pounds to kilograms. So step number 1, I have 8 ounces, and the equivalent statement is that there are 16 ounces in 1 pound. So I'm going to multiply by a conversion factor with ounces on the bottom and pounds on the top. So 16 ounces to 1 pound. Check to make sure the units cancel, the ounces cancel, the pound is left over. The answer is 0.5 pounds. Now that's just the 8 ounce part. So I need to say 7.0 pounds plus 0.5 pounds. And this gives me a total mass of 0.5 pounds. And I'm looking at my significant figures here because each one of these has a value in the tenths place. And I look at the area of least precision, then I get to keep this 0.5, which is a good thing because it's a valuable part of our problem. Okay, so step number 2. Now I have 7.5 pounds, and I'm going to multiply by a conversion factor. 2.205 pounds equals 1 kilogram. That's actually the equivalent statement. I need to put pounds on the bottom and kilograms on the top. So 1 kilogram on the top, 2.205 pounds on the bottom. And I'm going to check my units. The pounds cancel, the kilogram remains. So that's great. That's what I want. When I do the math, 7.5 divided by 2.205 gives me 3.40. There's a 0 after it. I'm only going to keep 2 significant figures because this has 2 sig figs. Now we're doing a division. My answer is 3.4 kilograms to 2 sig figs. In another example, this is a concept check actually. I'd like you guys to work this out. An individual donates 1.0 pints of blood. How many liters does this correspond to? So what do we know? 1.0 pints. And what's unknown is how many liters is that? There are 2.113 pints for every 1 liter. So go ahead and try this. And if you're not sure where to start, fast forward and I will do this example. My concept map is to go from pint to liters. That is the equivalent statement on the top. So I'll be starting with 1.0 pint. And I'm going to put liter on the top because that's what I want, and pint on the bottom because that is what I want to cancel out. So 1 liter on the top and 2.113 pints on the bottom. I'm going to check my units. Pints cancel, keep the liters, and liters will be in my final answer. So I go 1 divided by 2.113, and I get a value of 0.473 ... liters. I'm going to look at my significant figures. I have 2 sig figs here in the number 1.0. I have 4 significant figures here in 2.113. This is not an exact number, so I'm just going to look at the sig figs, and I have a lot more than I need. I only can keep 2 significant figures, so I'm going to round that number to 0.47 liters, and that will be my answer to 2 significant figures.